So we have learned about the idea behind dimensional analysis, and I believe now it's time for us to really get into dimensional analysis. Okay, so I'm going to provide you with a scenario which I think can be useful for us to apply dimensional analysis. So I'm trying to show you why do we need to know how to do dimensional analysis. Okay, so from there you can see what's the purpose of doing dimensional analysis and how can you benefit from it. Okay, so today imagine you are in a lecture, let's say by me. Let's say I have a messy handwriting on the whiteboard and you can't really catch what I'm writing. Okay, I'm teaching kinematics of linear motion. There's a lot of equations there and you can't really catch what I'm writing. So in that situation, what do? You ask help from your left neighbor, you ask help from your right neighbor. So you borrow their notes, you try to check whether your equation is correct or not. So on your left, there's Andy, let's say. So Andy written down this equation here. V is equals to U plus AT squared. Okay, so just to be really sure whether you copy the correct equation or not, you ask your right neighbor as well. And on your right, there's Karen. Oh, ha! Both Andy and Karen has written down a different equations, and of course, all three of you are now in a confusion. Which equation is actually correct? Actually, but you remember from chapter 1, right now, exactly right now, Mr. Gunn have actually briefed you all about there's 3 criteria that you need to follow in order for an equation to be valid or meaningful. So these are the 3 criteria. So you think, maybe I can use these 3 criteria to check whether the equation is valid or not. And that's what we are going to do right now. So let's start with Andy's work first. Andy's V is equals to U plus AT squared. So to be very clear with our dimensional analysis, let's define a few terms first. U is initial velocity, V is final velocity, A is acceleration, T is time. Okay, though this stuff you have actually learned before in SVM, but you learned about it in chapter 2 as well. Okay, so what we're going to do, our first step should be determine the dimension of each term. What do we mean by each term? Term is like V, like U, like AT squared. Okay, AT squared is a term, U is a term, V is a term. Basically, things that are separated by an equal or a plus sign or minus sign, you can think of it as a term. Okay, so we need to find the dimension for V, for U, for AT squared. So let's do it one by one. For V, you know that it's velocity. You know that velocity is displacement against time. So displacement is the most basic you can go. So displacement is having a dimension of length. Time is having the dimension of time. So you know that the dimension for final velocity should be LT negative 1. Then now you move on to U. U is initial velocity, so the logic should be the same as below. Velocity, displacement time, length, time. So you know that the dimension for initial velocity should also be LT negative 1. Whereas for the last one, AT squared, here is a little bit different. It's different from V and U. So let's do it slowly. AT squared, we can break A and T squared because A and T squared are multiplied together, right? So we can break it into A and T squared. Okay, so that's the first step, break it into its components. So let's find the acceleration, the dimension of the acceleration. Acceleration, it's velocity against time. So velocity against time, we know that it's LT negative 1, we've learned from up here. Then time is T. Okay, so if you combine them, you get LT negative 2 because T negative 1 divide by another T, that will be LT negative 2. And multiply by T squared, we are not finished. We still have T squared. T squared, well, the dimension is just big T squared. So now if you multiply both of these things together, back together, we will get L. Okay, so that's first step. You determine the dimension for all the terms in the equation. Then what do you do next? You analyze the dimension according to the rules or criteria actually. So what are the criteria? Well, these are the criteria. So let me bring the dimension upwards so it's easy to do our analysis. Okay, so these are the three criteria. Well, from here you can see that U and AT square are having different dimensions. If you're having different dimensions, criteria 3 tells you that if you have different dimension, you can only multiply or divide. But what am I doing here? I'm doing an addition. So in this case, it's actually not obeying criteria number 3 right now. So we can say that this one yeah, actually it's number 3. Number 3 can only be divided. Yes, we have already disobeyed this one. And same dimension can only be added. Well, it's the same thing. Yeah, it's wrong as well because yeah, you cannot add things of different dimensions. So basically 2 is not followed, 3 is not followed already. And because of that, you can't really follow number 1. Because if you can't add up these two things of different dimension, you can't have the same dimension for the left hand side and the right hand side. So in this case, you know that Andy's equation, it's not dimensionally homogeneous. Okay, we say dimensionally homogeneous. What does it mean is homogeneous means same. Dimension, same. Not same dimension. So the left hand side and the right hand side are not having the same dimension. Thus, Andy's equation is impossible to be true. Well, impossible to be true, another word is false. Okay, so let's move to the right neighbor, Karen. Karen is V is equals to U plus half AT. So let's try to analyze her equation. Well, V and U we don't need to analyze anymore. It's the same as Andy's equation. But now instead of AT squared from Andy's, Karen writes half AT. Half AT, we need to do a analysis to determine its dimension. Okay, we can break it into smaller parts by splitting it into A and T. As you can see here, half is missing. Why half is missing? Because half is not really a measurement. Half is just a value, a coefficient. It's not measuring something, so it does not have any dimension. We also call it by the word dimensionless if something has no dimension. So in this case, we can just ignore the constant, the coefficient half, and focus on AT. So AT, we know A is LT negative 2. We have actually analyzed it in Andy's equation. T is big T, time is big T. So if you multiply together, you get LT negative 1. Now seems like everything is smooth. Let's bring up all the dimensions up here. And let's go through to the second step. Second step, we should be analyzing. I didn't change the title here. It should be step 2. We need to analyze according to the criteria that we have. Sorry, I didn't change this step over here. Okay, so these are the 3 criteria. Let's see. U plus half AT, they have the same dimension. So if they have the same dimension, they can be added or subtracted. So we can combine their dimension together. So now in this case, number 2 is follow, number 1 is follow, because the left hand side of the equation and the right hand side of the equation have the same dimensions. Well, number 3 is not really relevant because we are not really multiplying anything. Well, yeah, there's multiplication actually. A and T are multiplied together and they have different dimension, but we use multiplication. So there's no problem with that. Our focus is 1 and 2 for now. But the main idea is 1, 2, 3. All 3 criteria are followed right now. So this is called a dimensionally homogeneous equation. Okay, and in this case, we can say Karen's equation is possible to be true. Okay, so possible to be true. Okay, I didn't write true, I wrote possible to be true because there's something I need to discuss after this. Okay, so we have analyzed Andy's equation and it's not dimensionally homogeneous, impossible to be true. You have analyzed Karen's equation. Karen's equation is dimensionally homogeneous and it's possible to be true. I put a tick here because it's dimensionally homogeneous. But I have something I would like to ask. Does dimensionally homogeneous equivalent to a correct equation? If an equation is dimensionally homogeneous, does it mean it's correct? Okay, so this is the thing I wish to investigate. In this case, I shouldn't put a tick sign. I should change it to a question mark, whether it's correct or not. So to make things even more complicated, you've asked the neighbor in front of you to provide you with his equation. And the neighbor in front of you is Alicia, and this is her equation. V is equals to U plus AT. And if you do go through the step 1 and step 2, you'll find that Alicia's equation is also dimensionally homogeneous and it's possible to be true. Now you have Karen's, you have Alicia's equation. Both of them are dimensionally homogeneous. But which one is really true? Well, you don't know actually. That's the limitation of dimensional analysis. Dimensional analysis allows you to check whether the equation is possible to be true or not. But it doesn't really tell you whether the equation is true or not. In this case, it is still a mystery whether Karen's equation is correct or Alicia's equation is correct. But for sure, you know that Andy's equation here is incorrect. That's the usefulness of dimensional analysis. Okay, so I'd like to sum up in this sentence. Dimensionally homogeneous doesn't mean the equation is true. It only means that there's a possibility that it is true. It's not a must to be true. It only suggests a possibility that it is true. Okay, so well, to solve the mystery, you ask your teacher what equation is he writing on board. So I will tell you that what Karen has written here is actually wrong, but Alicia's equation here is correct. Well, that one you can't really figure out using dimensional analysis. So I hope you get the idea of dimension analysis. What is its potential? What can it do? And what is its limitation? Not being able to check whether the equation is correct or not.